Okay, welcome back to Calculus and Linear Algebra. We're still in Module 1. This is week number 3. Today we'll start introducing matrices and their operation. It's linked to the second, let me say, course learning outcome, which is identify and calculate the matrix operation and use them to solve system of linear equations. We will talk about the principal, operation, and determinant. We will use the same way. Now you remember this movie Matrix, right? It's coming from here, from these matrices. Okay, you enjoy the movie, let's enjoy the matrix. Now I will start with the idea behind matrix. You see, matrix usually represented in this way: A equal, as example, two large brackets and number, set of numbers, different set of numbers. From where it came? Actually, it came from, when we have equations, two equations with two unknowns, x and y, we learn how to solve them simultaneously by elimination, by substitution. But what we have if we have four equations similar to this? What we have if we have million equations? It's really difficult. But we can solve them by using matrices. How? By converting these equations into matrices. And there is rules controlling the dealing with matrices, which make your task as an engineer very easy and direct. Okay, so matrix is array which have number of rows and number of columns. These are the rows: row number 1, row number 2, and so on. You see, 1, this first name, when you say here A1, it means row number 1. Let me say 3 here, it means column number 3. So you see, 1, it means the row is number 1. Here the row is number 3. Okay, the first number represents the row, the second number represents the column. As example, this column, you see here, column 3, but row number 1, row number 2, row number 3, and so on. It can be simply written in this way: Aij, which is m by across n. M is the row and n is the column. This is the matrix. You can see this is the row, this is the column, and the matrix represented by its size, m cross n, rows by column, which represent the size or dimension. Now let me start with some definition related to matrices. I will define well-known matrix, which is called square matrix. Square matrix, when rows equal columns, we call it square matrix. As example here, row number 1, 2, 3, 3 rows. I will say 3 times. Column 1, column 2, column 3, 3. Since rows and the columns are equal, then we say this is square matrix. Now if he ask me the order, I will say it's 3 by 3. If he ask me about the elements of diagonal leading diagonal, it means this is the diagonal. So if he asks me about the leading diagonal, it will say 8, 9, 3. If he asks me as example to find A2, 3, it means row number 2, column number 3. Just a minute. This is row number 2, this is column number 3, so this is the number, which is 8, and so on for other elements in the matrix. Second definition is for diagonal matrix. Diagonal matrix is a matrix which have only diagonal values in the diagonal. Every element else will be 0. You see here, Aij is 0. Only when Aii, it means 1, 1, 2, 2, 3, 3, it have values. Okay. Example. So see this matrix? This matrix here 0, 0, 0, great, 0, 0, but here 5, no, this is not diagonal. Okay, this is the diagonal. There is value here, this is not the diagonal. Here 0, 0, 0, 0, 0, 0, only diagonal. This is diagonal. Here 0, 0, 0, 0, 0, 0, great, this is diagonal. No, just a minute, there is 0 on the diagonal. We cannot say this is diagonal matrix. You see here? So diagonal matrix when we have only the diagonal elements. Scalar matrix. Scalar matrix is a diagonal matrix, but the diagonal elements are the same. As example, this is 2 by 2 matrix here. You see the diagonal have the same value, which is 2. The diagonal here have the same value, which is 4. The diagonal here, oh, there is a 3, 4, 4, 3. So this is not a scalar matrix. This is diagonal, but not scalar matrix. Another definition, identity matrix. Identity matrix is a square matrix also, okay? But it's diagonal and it's a scalar, but its value is 1. The value will be 1, okay? This is diagonal, identity matrix. But the second one here, it's not identity because it's not square already. The same thing here, it's not square. This is 2 by 3. This is 3 by 2. So it's not diagonal matrix, not identity matrix. Now, zero matrix. Zero matrix is a matrix which have 0 for all elements. As you can see here, these are elements with zeros. Negative matrix. Negative matrix is the same matrix but multiplied by -1. It means all elements will be in negative. As example, this is A. I want the negative of A. I will make every element with minus sign. You see here? All elements multiplied by minus. The same thing for B. It will be -2, -4, -3, -1, the other zeros. Now, upper triangular matrix. Upper triangular matrix is when the numbers is only in the upper triangular. You see here, this is square matrix. It's at the end square, supposed to be square. Here we have numbers, and the down triangle will be 0. This is called upper triangular matrix. And there is also lower triangular matrix where we can see here from the diagonal down there are numbers, but the upper triangle will be zeros. This is called lower triangular matrix, means the numbers are in the lower parts. Now transpose of matrix is done by changing rows into columns and columns into rows. As example, you see this is A, it's transpose. You see this simple T, it means transpose. This row will be column. The first row will be the first column. The second row will be the second column. The third row will be the third column. The same thing here. This is the first row, it will be the first column. The second row, the second column. The third row, the third column. Okay? This was 3 times 2. The new one will be 2 times 3. I change columns into rows. Symmetric matrix. Symmetric matrix is the matrix which have transpose equal to the original matrix. As example, you see this is A. It's a transpose. This row will become the first column. This row, the second column. This row, the third column. But have a look at them. It is still here. You see 4, 2, 3, 2, 5, 6, 3, 6, 7. It's the same. So we say this is symmetric matrix. Also, don't forget this is square matrix. Skew matrix when we do the transpose and we find that the new matrix is negative matrix of the original. As example, this matrix here A. You see, when I find the transpose, this is the first row, it becomes the first column. The second row, the second column. The third row, the third column. And I compare between them. I found transpose become minus A. All elements the same in their same places, but with minus sign. Now, row echelon form happen when we satisfy 3 conditions. The first condition say, have a look, where all 0 rows, it means rows with 0 elements, no numbers, if there any, because sometimes there is no 0 in the it could be row echelon form, but it doesn't have 0 rows, supposed to appear at the bottom. As example, you see here, this is 0 row, appear at the bottom. This is 0 row, appear at the bottom. You see here? The second condition is satisfied. The first non-zero entry from the left of non-zero is a number 1. This entry called leading 1. As example here, this is the first row, started with 1. The first row started with 1. The first row started with 1. I don't count here 0. If it is number, it should be accounted, but 0 is not accounted. Okay. The third condition, for each non-zero row, the number 1 appear to the right of leading of the previous row. As example, here, this row, the first row, the second row should start 1 degree, or let me say 1 place behind with 1. I mean here 0, here 1. You see here 1, it's supposed to start here 0 0 before. Here 1, now this is not correct because it started with 1. It's supposed to be here, right? 1 degree behind. So the previous, let me say, matrices, this one is not row echelon because of this one. The second one is row echelon because, as you can see here, 0 row down. The first row started with 1, the second row 1 degree behind, and so on. And the third one is also the same thing. These are the 0 rows. The first row started with 1, the second row 1 behind, and the third row 1 behind. Now, what about reduced row echelon form? The same previous 3 conditions, we will add 4th condition, which say if the column contains a leading 1, then all other entries in the column are 0. This is, say, reduced echelon form. Example, see this one, okay, is reduced row echelon form. Why? Because you can see here, but there is no 0 rows, so it's okay. Here the first row started with 1, the second row 1 degree behind, the third row 1 degree, but all elements here are zeros, only the diagonal. So this is called reduced. The second one, okay, you can see here these are the 0 row at the bottom, and here we started with 1, here 1 degree behind. The third one, here we have -1, so we cannot say this is reduced echelon form. Got it? Okay. Now, if we have two matrices A